Today we are going to continue our lesson about mole concept for Part D. Learning outcomes. At the end of this topic, students should be able to define for each of the following concentration measurements: molarity, molality, mole fraction, percentage by mass, and percentage by volume. Concentration units. When an amount of solute dissolves completely in a solvent, it will form a homogeneous mixture called solution. The common terms that you have to understand before we go further are solute. Solute is the substance being dissolved and present in the smaller amount. Solvent. Solvent is the substance doing solving and present in the larger amount. Solution. Solution is a homogeneous mixture of two or more substances that form when amount of solute dissolves completely in a solvent. Concentration. Concentration is the amount of solute present in a given quantity of solvent in a solution. Have a look at example 1. We have water and add with sugar. We will form a sugar solution. So what is solute and solvent? Solute is a sugar, while solvent is water. Expression of concentration. There are several ways to represent concentration of a solution. Molar concentration or molarity, molar concentration or molality, percentage by mass, percentage by volume, and mole fraction. The first one is molarity. The symbol is capital letter M. Molarity is the number of mole of solute dissolved in 1 liter of solution. The unit that we can use is mole per liter or mole per decimeter cube or molar. The formula for molarity equals to mole of solute in mole divided by volume of solution in liter. Example 2. Given 1.46 molar glucose or 1.46 mole per liter glucose, it means that it has 1.46 mole of glucose, which is solute, dissolved in 1 liter of the solution. Next is molality. Molality is the number of mole of solute per 1 kilogram of solvent in a solution. The unit is mole per kilogram or molal or small letter m. Formula for molarity is equals to mole of solute in mole divided by mass of solvent in kilogram. Mass of solution is equal to mass of solute plus mass of solvent. But volume of solution is not equal to the volume of solvent. Mole fraction. The symbol is capital letter X. Mole fraction is the ratio of the number of moles of one component to the total of number of moles present. The formula for mole fraction of A is equal to mole A divided by mole total, where mole A is equal to number of mole of component A in the mixture, while N total equals to total number of moles in all components in the mixture. If a solution containing A, B, and C, mole fraction of A equals to mole A divided by mole A plus mole B plus mole C. Or we can use mole A divided by mole total. Remember guys, no unit for mole fraction. Mole fraction always smaller than 1.000 and total mole fraction in mixture equals to 1.000. Percentage by mass. Percentage by mass is the ratio of the mass of solute to the mass of the solution multiplied by 100. Here the formula. Percentage by mass equals to mass of solute in gram divided by mass of solution in gram multiplied by 100. Or we can use mass of solute in gram divided by mass of solute plus mass of solvent in gram multiplied by 100. Here, mass of solution is equal to mass of solute plus mass of solvent. Let me look at example 3. Given that 10% by mass of sodium hydroxide in the solution. According to the formula percentage by mass, the mass of solute in gram divided by mass of solution in gram multiplied by 100. It shows that 10 grams of sodium hydroxide dissolved in 100 grams of solution, or 10 grams of sodium hydroxide dissolved in 90 grams of solvent, which is water. Percentage by volume. Percentage by volume is the ratio of the volume of a solute to the volume of the solution multiplied by 100. The formula for percentage by volume is volume of solute divided by volume of solution multiplied by 100. It most often used for liquids and gas. Helpful tips. For questions that give concentration and density, we can make assumptions based on concentration. For molarity, since the formula involves the volume of solution in liter, hence we can assume volume of solution is equal to 1 liter. For molality, since the formula involves the mass of solvent in kilogram, we can assume mass of solvent equals to 1 kilogram. For percentage by mass, since the formula involves the mass of solution in gram, we can assume mass solution is equal to 100 gram. And the last one, percentage by volume, since the formula involves the volume of solution, we can assume volume of solution equals to 100 milliliter. Let me try this exercise. Given 0.05 mol zinc powder is added to 10 milliliter hydrochloric acid to form a zinc chloride solution. The question is, define the molarity of zinc chloride solution. You are given 30 seconds to choose the correct definition for the situation.
Like a bird on a tree, I'm just sitting here. I got time, it's clear to see. From up here, the world seems small. We can sit
Okay, the answer is B. 0.05
so
mol of zinc
beautiful.
dissolved in
You and
0.01
me,
liter zinc chloride solution.
we meant to be.
1.3 Stoichiometry Learning Outcome. At the end of the lesson, you should be able to A. Write and balance chemical equation by inspection method, and write and balance redox equation by ion-electron method. B. Define limiting reactant and percentage yield. And C. Perform stoichiometric calculation using mole concept, including limiting reactant and percentage yield. So, what is stoichiometry? Stoichiometry is a quantitative relationship between reactant and product. The most important thing in stoichiometric calculation is balance chemical equation. Balancing chemical equation. Chemical equation is a shorthand expression for a chemical reaction. The reactant are written on the left side and the product on the right side of the equation. Look at the general equation given. So XA react with YB, produce ZC and WD. So actually X, Y, Z and W are stoichiometric coefficient. Stoichiometric coefficient refer to the number that we use to balance the chemical equation. A and B are reactant, whereas C and D are product. To balance the chemical equation, we have two methods. The first method is inspection method, and the second one is ion-electron method. For the lecture, we just cover for inspection method only. To balance the chemical equation by using inspection method, we need to follow a few steps or rule as a guideline. The first step is write down the unbalanced equation and remember, write the correct formula for the reactant and product. Step 2. Balance element or atom. Okay, to balance element or atom, first we need to balance the metallic element first. Next, followed by non-metallic atom or element. After that, balance the hydrogen and oxygen atom. Step 3. Check to make sure that the total number of atoms of each element is the same on both sides of equation. Let's try the step for example 1. So according to the equation given, ethane react with oxygen gas to produce carbon dioxide and water. So remember, the first step, we need to write unbalanced equation. So this one, unbalanced equation. Make sure you write the correct formula for ethane. C2H6, oxygen gas O2, carbon dioxide CO2, and water H2O. Okay, that is first step. Second step, we need to balance atom. So we need to balance metallic atom first, followed by non-metallic atom. So in this case, there are no metallic atom. So we start with non-metallic atom. Okay, so non-metallic atom is carbon. So let's start with carbon atom. So you need to count number of carbon atom on left side and right side. For the left hand side, 2 carbon atom, and right hand side, 1 carbon atom. So we need to balance carbon atom. To balance the carbon atom, we need to write 2 in front of CO2, carbon dioxide. Next, balance hydrogen and oxygen. So left hand side, the number of hydrogen atom is 6. Right hand side, 2 hydrogen atom. So to balance hydrogen atom, you need to write 3 in front of H2O. So we get 6 hydrogen atom on both sides. Okay, next, balance oxygen atom. So on the right hand side, number of oxygen atom is 7. Left hand side, 2 oxygen atom. So to balance oxygen atom, we write 7 over 2. So we get 7 oxygen atom on both sides. So we get balanced equation for the reaction of ethane with oxygen gas to produce carbon dioxide and water. Okay, step 3. Check to make sure the total number of atoms of each element is the same on both sides. So, left hand side reactant, right hand side is product. So for the reactant, 4 carbon atom and product 4 carbon atom. Reactant 12 hydrogen, product 12 hydrogen. And then reactant 14 oxygen and product 14 oxygen. So total number of atoms on both sides are equal. So that means we get balanced equation. Example 2. The reaction of aluminium with sulfuric acid produces aluminium sulfate and hydrogen gas. Step 1. Write unbalanced chemical equation with correct formula. Aluminium Al, sulfuric acid H2SO4, aluminium sulfate Al2SO4 3, and hydrogen gas H2. Step 2. Balance atom. So aluminium is metallic atom. So let's start with aluminium. So on the left hand side, 1 aluminium atom. And on the right hand side, 2 aluminium atom. So to balance aluminium on both sides, so we need to write 2 in front of Al. Next, balance non-metallic atom, sulfur. In this situation, sulfur and oxygen can be balanced together as a unit because it is polyatomic ion. But if you having problem to identify polyatomic ions, you can balance sulfur and oxygen individually. Let's try to balance sulfur and oxygen together as a polyatomic ion. On the left hand side, 1 SO4 2- ion. On the right hand side, 3 SO4 2- ion. So to balance SO4 2- ion, we need to write 3 in front of H2SO4. Next, balance hydrogen. On the left hand side, 6 hydrogen atom, and on the right hand side, 2 hydrogen atom. To balance hydrogen atom, we need to write 3 in front of H2. Step 3. Check to make sure the total number of atoms of each element is the same on the both sides. So reactant, left hand side, and product, right hand side. So for the reactant, there are 2 aluminium atoms 6 hydrogen atom, 3 sulfur atom, and 12 oxygen atom. For the product, there are 2 aluminum atom, 6 hydrogen atom, 3 sulfur atom, and 12 oxygen atom. So the total number of atoms of each element on the both sides are equal. So that means the equation was balanced. Exercise 1. In 2 minutes, balance the following equation. Check your answer. Exercise 2. In 5 minutes, balance the following chemical equation.
Hi, in this video we're looking at this concept of limiting and excess reactants. Now don't forget, a reactant is an ingredient. It's something on the left side of the equation. And a limiting reactant is something that gets used up first. An excess reactant is something that is left over. So let me kind of show you this visually. Let's say I had this generic equation, A plus B makes AB. And I've got all these A's and B's on the screen here. Let's say this is in a beaker. This reaction starts to take place and AB starts being formed, but then it stops right here. And that's because there's no more A to react. I have plenty of B left over. In fact, we'd call this our excess reactant, and A would be called the limiting reactant. And reactant A is the limiting reactant because it's used up first and therefore limits how much of the product can be made. So that's what a limiting reactant is. It's a reactant that is completely used up before all of the other reactants in a chemical reaction. Now here's a different way to look at this. Let's say I had two reactants on the left, two products on the right. This is all happening in one container. And I just want to kind of use this little bar graph to show the quantities relative to each other of all of these four substances in a beaker. So I start the reaction, I'm producing products, I'm getting rid of reactants because they're turning into products. But it looks like reactant 2 is reacting at a little bit of a faster rate. And oh, we're done. We're done because reactant 2 is gone. It's turned into product 1 and 2 with some sort of combination with reactant 1. That part's irrelevant. What's relevant is the fact that we don't have reactant 2 anymore, so therefore the reaction has stopped. Even though I have an excess amount of reactant 1 and I've got plenty of products, we're done. So reactant 2 is the limiting reactant, and in this case, reactant 1 would be considered the excess reactant. So let's do an example problem here. This is ammonia reacting with oxygen to produce nitrogen monoxide and water. And the question says a 2-gram sample of ammonia, so 2 grams of this, is mixed with 4 grams of oxygen, so 4 grams of that. And then it asks, which is the limiting reactant? So here's how you do this. Pick a reactant, and it does not matter which reactant you pick. For this example, I'm going to choose oxygen. You could start with NH3 and you'd be getting the same conclusion of which of these two is the limiting reactant. I'm going to start with oxygen. So you pick a reactant, and then what you want to do is calculate how much of the other reactant is used when all of that mass is used up. So if I have 4 grams of O2, I want to do a mass-to-mass stoichiometry calculation to figure out what mass of NH3 would react completely with this 4 grams of O2. So on the bottom, I want the molar mass for oxygen. That's 16 for each oxygen times 2 is 32 grams of O2. That's the mass of 1 mole of O2. So I've canceled out grams of O2. My next stop, if you remember from the mass-to-mass stoichiometry video, is a molar ratio. So on the bottom, I want to look for the coefficient in front of O2. It's 5. So that means 5 moles of O2 reacts with 4 moles of NH3. So there's my molar ratio. This gets me from moles of one substance to moles of another. And then my final stop is just to use the molar mass of NH3 to figure out what mass of NH3 we're talking about. So a mole of NH3 weighs what? Well, a nitrogen is about 14. A hydrogen's about 1. There's 3 of them. So 14 plus 3 is 17 grams of NH3. You know, the more precise molar masses you can use, the better your results will be. But to illustrate this, I don't need crazy specific molar masses. Okay, now I'm ready to calculate. So I've got 4 grams times 4 times 17 over 32 over 5. I'm skipping over the ones because they don't change your math too much. And what I end up with is this. 1.70 grams of NH3 is needed. Well, let's look at how much NH3 is available. 2 grams. Well, that's more than 1.7 grams, and that's all I need to react all 4 grams of oxygen. So what that means is NH3 is my excess reactant, and O2 is therefore my limiting reactant. All 4 grams of O2 will react with only 1.7 grams of the other reactant. There's more of the other reactant there. So that's how I know this is my excess reactant and this is my limiting reactant. Now, a very common follow-up question to this is this: how much of the excess reactant is left over? And in this case, all you really have to do is compare the amount of your excess reactant to how much of the excess reactant was needed. I have 2 grams present. I only need to use 1.7 grams, and so this just becomes 0.30 grams left over. Let's do one more question about this. It says, how much water can you produce given these reactant quantities? So I had 2 grams of this and 4 grams of this, and I was able to determine that this was my limiting reactant, LR for limiting reactant. If it's asking how much of a product you can make, and you're aware of which reactant is the limiting reactant, you want to calculate how much of the products you can make from the limiting reactant, not from the excess reactant. Here's why. The limiting reactant is going to run out and limit how much of the products you can make. So you want to use this mass in this example, 4 grams of O2, to calculate how much water you can make. So let's just do one more mass-to-mass stoichiometry problem. 4 grams of O2, I'm going to multiply by the molar mass. In this case, the molar mass is on the bottom, so 32 grams of O2 there, 1 mole of O2 on the top. It should all look identical to your first setup here. On the bottom, I want 5 moles of O2. This is the molar ratio, this fraction here. So 5 moles of O2 to, in this case, 6 moles of water. And then the final fraction is the molar mass of water, so that I can cancel as I go here. And now I'm in moles of H2O. On the bottom is going to be 1 mole of H2O. And then on the top is going to be the mass of that 1 mole of H2O, which is what the molar mass is, 18.02. 18 is probably just fine as well. Okay, so let's do one more calculation. 4 times 6 times 18.02 divided by 32 divided by 5 gives me 2.70 grams of water. What did we just calculate for? Well, the question asked us, given these reactant quantities of 2 grams of this, 4 grams of that, how much water can we make? And we chose the limiting reactant to do our stoichiometry calculation with because that's what's going to be completely available. All 2 grams of this is not going to be used up because this 4 grams of O2 will run out. So I want to use the limiting reactant to do this calculation. When I run that through, I get that I can make 2.70 grams of water. So that's it. That's limiting and excess reactants. In some reactions, you'll get a reactant that limits the process. And that means that all the other reactants are in excess, that there's some left over. It's kind of an interesting concept. And maybe the most cost-efficient way to set up a chemical reaction is to do the calculations for your reactants in advance so that you're mixing together exactly the right numbers of your reactants so that you don't have a limiting or excess reactant in the end. All you have is product. I hope this helped. Thank you.
(1.3b) Define limiting reactant and percentage yield. Definition of the limiting reactant is reactant that is completely consumed in a reaction and limits the amount of product formed. So, limiting reactant is the reactant used up first in a reaction or reactant that completely consumed before other reactant. This limiting reactant determines the amount of product formed because when the limiting reactant completely consumed, the reaction was stopped. Let's use simple analogy to understand more about limiting reactant, the cheese sandwich. To make one cheese sandwich, we need to have 2 slices of bread and 1 slice of cheese. So, bread and cheese are reactant and cheese sandwich is product. The stoichiometry ratio to make cheese sandwich are 2, 1, 1. 2 slices of bread react with 1 slice of cheese to produce 1 cheese sandwich. Let's say we have 9 slices of bread and 3 slices of cheese. Which one is limiting reactant, bread or cheese? Let's figure out the answer. 2 slices of bread need 1 slice of cheese to produce first cheese sandwich. Another 2 slices of bread need 1 slice of cheese to produce second cheese sandwich. Next, 2 slices of bread need 1 slice of cheese to produce the third cheese sandwich. Now we got the answer. The limiting reactant is cheese because completely consume and limits the cheese sandwich production. And slice of bread is called excess reactant because remain after the reaction. Definition of the percentage yield. Percentage yield is the percent of the actual yield of a product to its theoretical yield. The formula of the percentage yield is percentage yield equal to actual yield divided by theoretical yield times 100%. Actual yield is the amount of product actually obtained in a reaction, and theoretical yield is the amount of product predicted by stoichiometric calculation. That's all. Thank you.